Alright, we're going to get started. It is with my pleasure that I get to introduce Dr. Marilyn Carlson from Arizona State University. She was actually my advisor when I was there, my major professor, so I get to return the favor here and get to say a few nice things about her. Rather than start off within all the math ed accomplishments, I know she's very proud of her roots, so I thought I'd say a little bit about that. She's a proud farm girl from Cleveland, Missouri, am I right?
Yes.
Where she then attended Central Missouri State, right? She was a Jenny, actually an athlete there, the first superstar women's athlete of their university, according to their website.
How did you find that out?
I'm a good Google. Young generation can go Google. So let's see, what else they say about her. She was a Hall of Fame inductee in 1995 or so. Won their first senior female athlete award in basketball and track. Four-time All-American, is that right?
6.
4 for track, 2 for basketball, or something like that?
No, 6 for track. I
Oh,
think you
6
got
for track.
the top 5.
Oh, she still holds 4 track records for their university and is ranked in the top 10 in 6 different track records. So, not only an impressive math educator, but also a well-rounded athlete. Let's see, now back to the stuff you guys will probably care more about, the math education stuff. Got her bachelor's in math education from Central Missouri State, then went to University of Kansas where she picked up a master's, not in math education, but computer science. Then felt the math education bug, I guess, again probably, and went back to her PhD in math education from the University of Kansas. Who will lose in basketball?
Who will beat Ohio State?
Also during the time when she was completing her doctoral degree, she was the director of first-year math at the University of Kansas for 10 years. Then she served as director of first-year math at Arizona State University from 1995 to 1999. Other than that, she's also been the coordinator of Sigma on Room, the research and undergrad math ed community. She was the coordinator of that. Also a research mentor for that community as well. Some other things that she's been awarded is a career grant, and that's one of the most prestigious grants that they give. She was awarded that to support her research on students' understandings and kind of development of curriculum from that. Some of the research that she's done has ranged from seminal works on students' understanding and function, co-relational reasoning, which I know some of the in my class, we talked about that. She's done some of the pioneering works in that as well. I'm sure she'll speak a little bit on that today. She's also does some pretty strong work in students' problem-solving activities as well as experts, mathematics experts' problem-solving activity, comparing and contrasting those two populations. And lately she's been really involved in developing curriculum and trying to help secondary teachers support their students' learning in mathematics, particularly at the pre-calculus and calculus level, which is a lot of what her talk will focus on today. So rather than me take up any more of her time, I would thank you for coming.
Thank you for that very nice introduction, and I just want to tell you people at the University of Georgia that you should feel very grateful to have gotten one of ASU's top PhD students, so take good care of him. And I know you guys that are in his math class for secondary math class, content math class, whatever it's called, that you've had the luxury of benefiting from Kevin. So anyway, Kevin, thank you. Now can I go run and track and track? Thank you for looking that up. I didn't even remember that. So anyway, so the context of my discussion with you today is a large NSF grant that we at ASU were funded on. I was the PI of the grant about 8 years ago now. And so our purpose of the grant was to improve secondary mathematics and science teachers' understanding of key ideas of pre-calculus that are foundational for understanding calculus. So a little bit about me. I did look at students' understanding of calculus for about 5 years before I delved into taking seriously how to support teachers and students, students to emerge with understandings of pre-calculus mathematics. And then once a group of us fleshed out learning trajectories and curriculum and iterated on our research relative to students' understandings, then we turned our attention to how can we support teachers to make the kind of shifts in their classrooms where they're engaging students in meaning-making, sense-making, constructing knowledge and understandings of ideas where they could apply them in novel contexts. So the first hurdle that we stumbled on in working in the schools was that the teachers' knowledge and understandings of the content were so very impoverished. The teachers had no image of how to engage students in their classrooms in ways where they would develop their ability to conjecture, argue, defend their answer. And so as we went into the classrooms in the first year, what we saw was very characteristic of the TIM study, that teachers, secondary teachers' image of secondary teaching, even in the best schools in Arizona, there was no different than the lower income schools, that it was stand and deliver teaching. It was like teaching kids how to get answers to problems. So we hypothesized initially that if we realize improvements in student learning, that we could then achieve shifts in student thinking. And so improvements in student learning was only possible if we first improved teachers' understanding of the content, right? You can't teach exponential growth if you don't understand it yourself. We also needed to give them experiences where they were engaged in graduate courses where they were actually exhibiting these mathematical ways of thinking that are well documented in the literature. And I'm not going to detail these. I'm sure that most of you graduate students have read the work on problem-solving mathematical practices. Also, we knew, too, that we needed to change the teachers' images of what classrooms look like. We didn't know much about how to do that, so we ended up drawing from the literature and putting some of interventions on the table that had been successful in other places. We had a 4-course graduate sequence, so you can imagine, you guys that had Dr. Moore's class, 4 courses that are developing your understanding of rate of change, covariational thinking, exponential growth. And after 4 graduate courses, you can imagine that the teachers were emerging with shifts in their understandings. But the challenge then is, even though they understood the mathematics better and we were seeing shifts in their ability to argue mathematically, exhibit the mathematical thinking behaviors, reasoning behaviors similar to a mathematician, the question was, keep in mind, we were funded to impact students, right? Okay, so part of the story is, well, how are we going to shift their classrooms? We started with professional learning communities. The teachers were in the driver's seat, they had their curriculum, we had no curriculum at that time, so we were there with all the best tools we had, which was a lot of knowledge about the processes of learning key ideas of Algebra 1 through pre-calculus through calculus, but we weren't equipped with kind of clear understanding of what kind of ways to support teachers in shifting their practice from stand and deliver to being student-oriented, conceptually oriented, and having this very high bar for ourselves because we have, like you all, the luxury of PhD students that have fleshed out the critical processes and issues of understanding exponential growth, trigonometric functions, and so forth. Those are the kind of images we had for the kind of understandings we thought the teachers should have and they should be promoting. We weren't just about, well, can the teachers ask a little better question? Are they going to put their students in groups and are they going to be more engaged more often? We were really looking through the lens of all of these frameworks that have been published in the literature that characterize what understanding looks like, and some of them characterize how understanding develops. So this process was the typical research project for the graduate students. This is no big deal, but for some of you high school teachers that may eventually get the bug to study learning, what do we do as researchers? We develop cognitive models. Dr. Moore is is the best in the world right now in having a cognitive model of how students come to understand angle measure, sine function, cosine function, connecting to trigonometry. So what he did was he looked at, just from analyzing the mathematics, what would that look like? And then he designed an intervention, curriculum intervention. He implemented it, he studied it, he revised it, and then he found out that, well, that initial framework wasn't quite right. A lot of it was right, so now we need to readjust our lens in terms of the hypothetical learning trajectory involved in understanding these key ideas of trig. And with the work that we've done with trying to figure out how to support teachers, we've had probably about 5 iterations of materials that we've developed. So, you know, and I see this process of refining, whether it be curriculum or how to support teachers, it never should stop. You know, we continue to learn more and more how to create richer classrooms with quality thinking and reasoning. And the more we learn, you know, we should continue to iterate. Primary findings of phase 1, which ended after the end of 5 years, that we did improve teachers' understanding key ideas. And we did a lot of work on how to get the PLCs to functioning effectively. And I'll point you to some papers if you want to read that. But Kevin, Dr. Moore, when he first came on, he was out with his camera videotaping PLCs. And, you know, everybody was doing PLCs. We got funded because PLCs were going to be the answer to the teachers reflecting on their practice in ways where all of this wonderful new knowledge they now had was going to be infused into their teaching. So we did find out, we learned a lot about the role of the facilitator and how easy it is for PLCs to be nothing but gab sessions. And just some of the key findings is facilitator has to be able to hold teachers' feet to the fire. They have to have rich conceptions of the mathematics themselves. So really a good facilitator is very much like a good teacher. You know, they've got to get everyone engaged. They've got to not allow people to give explanations that are incoherent. So it's a matter of getting the teachers to start to speak in ways that would be much more coherent in their classrooms, and to be able to justify their thinking. And then we shifted also then to start to look at student thinking. So they interviewed your students. We shared issues of how did that task work with our students. And what we found, after 5 years of spending quite a few million in NSF dollars, we found that it still wasn't enough. We went into the classrooms and they looked about, well, a little better than they did on day 1. And then we had in a school, Tempe High School, I was working with some of my wonderful teachers that we work all over the valley. But anyway, so we have various schools that we worked in. And some of the schools, the administration wasn't supportive of the kind of shifts that we wanted. So what would happen in those schools is 2 or 3 teachers would shift and get on a track where I think they could have made some pretty good progress. But the state exams, the district exams being all procedural and being tied to the teachers, math teachers' pay, actually that occurred in several schools, was a real deterrent to these teachers being able to stay on a road where they actually changed their curriculum in the ways that it needed to be changed. So, so we couldn't report any shifts in students at this point in time. This is after a lot of guided research interventions and a lot of studying what's going on with teachers. And then the school, so then we actually asked our NSF officer if we could work in a school that everybody was on board. And they said yes. And so we went after school, and we found out 2 years later, Kevin will remember this, that the principal said, yes, everyone's on board, only to tell me later that day 1 he called them in and half of them were on board. And then the second discussion with him, he told him how much work it was going to be, 3 years, and then only a quarter of them were on board. And then he told me, oh, they're all on board. And then he called the teachers in and he said, I don't care what you guys think. You're going to do it because this is good for you. So you can imagine the environment that we walked into on the first day in that class with those teachers. So our real issue, many of you graduate students, I'm sure you've read Deborah Ball and Hill's work on MKT in elementary, and there really isn't very much done on MKT for secondary. And so essentially what we mean by mathematical content knowledge for teaching, this was our image of what needed to be transformed in these teachers to allow them to make better decisions spontaneously in the class, to choose better tasks, to write better tasks. And we drew from Pat Thompson, who was an early PhD student here at University of Georgia, worked under Les Steffi. And one of his students at Vanderbilt, Silverman, had a framework that, and I'm only extracting a few items on the framework for the purpose of moving forward to get to kind of the punchline. So where we're going is trying to get you guys looking at how hard it is to shift teachers and how we need so much work to drill down. And so anyway, nudge me along if I'm not getting there. I think I'm doing okay. But anyway, so I'm kind of shortchanging some of the theoretical perspectives that guided our thinking in our early work. But certainly teachers need to develop a richer understanding. Yeah, absolutely. Next, according to Thompson and Silverman, teachers becomes interested in affecting student thinking. Les Steffi, you have all read about decentery. You know, it's Piaget and Les Steffi. They've got to read, but like, it's not just about what I say up here. It's about, oh, am I affecting your thinking? And then the teacher begins to attend to student thinking in some way. So they begin to be aware that it might be a problem that what I'm saying is not quite being constructed in a way that's as coherent as I think I'm saying it. So there might be a problem, but the teacher doesn't really quite know how to affect student thinking. And even though the teacher has this, and this is where Kevin and I are going to move ahead of that Pat Thompson guy. Pat probably will come back and say, oh, I was thinking that anyway. So that teacher develops richer understandings, and my conjecture now in working with these teachers that these richer schemes of meanings and understandings, they develop all the time. It's not like you get them to understand the mathematics, because at the end of these graduate courses, they had a lot better of an understanding, but relative to mathematical content knowledge for teacher, where a teacher begins to develop theories of how students might learn an idea, the issue is, well, what does that entail to develop a theory of learning? And what we're seeing right now in our project is that the connections, the mathematical connections and the images of how students might learn an idea, they feed into each other as you think more about students how to learn an idea and pedagogical ways to teach the idea. The connections among the teachers get richer and richer over time. And Kevin and I love telling the story that, you know, we wrote the curriculum, and every time I teach the curriculum, I get a problem thrown at me that I can't work my way through it in 3 or 4 minutes. So I'm I shouldn't say constantly, but you know, a good curriculum is scaffolded in a way where connections are made, problems have multiple solution paths, and students might think in ways that weren't even anticipated in the research. And so the teacher then is constantly having to adapt and adjust, you know, making connections that they didn't have before. So we see this whole issue of the teacher's mathematical content knowledge being interwoven with their theory of learning. Marty Simon and Silverman Thompson talked about key developmental understandings. I'm going to mention it mostly for the fact that, you know, several people have talked about Les Steffi's work in, you know, ways of thinking that lead to a rational number understanding and that are so powerful. Similarly, in our work, as we rethought and drew from our own research and others' research that there are some key developmental understandings that all of algebra through pre-calculus hang on. And so this is the description of what it means to be a key developmental understanding. And I'll come back and talk to you in just a minute about just covariational thinking, quantitative reasoning, and covariational thinking, how if you think that way, everything in pre-calculus can emerge by using that way of thinking. Even the algebraic structure, you know, and I'll show you how you can stop the covariation, you can factor, you can solve for. And in the context of, you know, thinking about quantities and how they change together, we'll visit some of the topics, and I'll give you a little more detail on, you know, how we operationalize that way of thinking. So you look at the teacher, they have mathematical content knowledge, have knowledge of student learning, that feeds into classroom choices. Classroom choices then affect their mathematical content knowledge, and this is a vicious cycle. Okay, so now we're at the end of year 5, maybe before it was year 4, in year 5, and we weren't having success yet in this school, even though the administrators were on board, the teachers became on board because they appreciated learning the mathematics. But again, once again, we went into the classroom, and I told Dr. Moore, I said, gosh, nothing's happening. And these teachers looked at me and they said, Marilyn, I don't have a clue how to infuse this new way of thinking in this graduate course into my teaching, because it doesn't look like my Larson, Hostetler, my Stewart, my whoever else books that have a lot of word problems, but they're, you know, compartmentalized into pretty much disjoint problem types. And they're really, if you look closely at them, it's hard to find an idea in a lot of the secondary books, that they're not about ideas. So then Dr. Moore then volunteered to go out, and he taught his 3 module, I think it was, whichever one it was, and the teachers got to sit there and watch their students arguing, reasoning, exhibiting these mathematical practices, emerging. You guys know, you've been there. I know you undergraduates. You know, angle measure. How could anybody not understand angle measure? And so the teachers stood and watched, and that was profound. Had we not done that, I'm not sure that we would be where we are today. So, and I always had, you know, this is why I miss Dr. Moore so much. He asked much better questions than I am. He was the best one to operationalize the ideal of our curriculum. So he was our A team that went out and, you know, modeled what our image was of what we wanted secondary classrooms to look like. So what we did, so I'll just back this up. So then we said, oh my gosh, the curriculum is so incoherent. We've been working for 6 years. We've spent, I hate to say how much in SF money, taxpayer money, and we still see zero change in students. So finally, Michael Ortman and I looked at each other and we said, there's no way we're going to see shifts unless we write curriculum. And you know, we had a lot of knowledge, and never in my career would I think that I was going to take a little detour and write curriculum, but it was a necessity. Otherwise, I was going to have to say, here you go, NSF, take your money back. There's no way that I can claim to have been successful with the funding that they gave us. So you look at these topics, pre-calculus, right? What do you notice? All about functions. They're all about defining relationships between quantities. They all, mostly, we can talk about how things change together, the rate of change. And, you know, and initially we didn't know that proportional reasoning was going to be so fundamental in one of the key developmental understandings. But in the second or third iteration, we recognized that students couldn't understand what it meant for me to walk across the room at a constant rate if they couldn't reason proportionally. You know, they had, what does it mean for someone to go at a constant rate? The teachers would say, oh, your speed isn't changing. I said, what? That doesn't tell me anything. What does it mean to go to a constant rate? Every time I walk for a second, I go 2 feet. I walk for 2 seconds, I go 4 feet. I walk for 1/10 of a second, I go 1/10 of 2 feet. So see the proportional correspondence? And that's how constant rate of change is used to find new points on a line. Instead of just using a formula, once the teachers can reason in that way, they can be given a point 2.7, 5.3, the slope, and oh, you want to find the y-intercept? Well, what do we know? The changes in the quantities are proportional, right? So you use that scaling on one, and the other one has to scale by the same value. So those are the kind of rich connections that teachers need to be able to support student understanding and connections. So anyway, so we set out to write this curriculum. Okay, so to dig a little bit, because if I don't dig, you won't get to where our problem is, and I want people to help us solve our problems. So we're going to take a detour and start with proportionality. I know a lot of you are doing work in middle school, and I thought that would be a good context. But keep in mind, everything we're doing, we did for every one of these ideas. So the first thing is, what is it? I don't know, maybe you guys have already read it. What does it mean for? What is proportionality? What is proportionality about?
Constant quotient.
Pardon?
A constant quotient.
A constant quotient. Okay, what's a constant quotient? So proportionality has a constant quotient in it, but so what? What does that mean? That doesn't tell me anything. I'm picking on you. So help me out. Anybody, help me out. What more? What does it mean? What is proportionality? I want to help you. Proportionality is, first of all, I'll give you, it's about two quantities. Okay? And that is oftentimes missed. Proportionality is about the values of two quantities changing in such a way that they remain in the ratio of them is a constant. So that's a lot richer than, and that's the image that's in textbooks. It's a ratio, it's a ratio. There's something you don't know. I get interviews and interviews with teachers. Okay, cross multiply, you find that answer. But to really be able to use proportionality and trig and related rate problems and calculus and wherever, you really have to have this image of, whoa, it's describing how two quantities change together, and they are proportional if they change together in such a way that their values, the ratio of their values is a constant. Their values are related by a constant multiple. So think of scaling on a map. 2.5 inches, 75 miles. Every time I go 2.5 inches, I go 75 miles. So you could find a constant multiple to multiply the number of inches by to get the number of miles. Can you represent that now as a ratio? Yeah. You can figure out what is the ratio of, what is the fixed ratio the two quantities need to be in. And then the other part that is often not leveraged and needs to be leveraged to solve a lot of problems is that if you recognize two quantities are proportional, what can you say about the scaling? Just like my constant rate of change. The time that it's taken me in seconds to walk from the end of that table and the distance that I've walked from the end of that table in feet, would you say they're proportional? Would you say that if I'm walking at 2 feet per second, is my distance from the table in feet proportional to my time from the table in seconds? Yes. How many say yes? Yeah. And why? James, I told you I'd pick on you.
Because if for any 2 times that you pick, if you divide the time you've been away from the table by the distance you traveled, you get the same value.
Yeah, so if you walked 1 second, you went 2 feet. I'm letting you off the hook a little bit there, but okay, if you go another second, you go 2 feet. And now if I go half a second, I went 1 foot, I go 1/75th of a second, I go 1/75th of 2 feet. Okay. So then, we wanted the teachers also to see this connection to linearity. Okay, so now, my slides got out of order. Okay, so now we're developing this curriculum, and this curriculum entails, some of you will be very familiar, these scaffolded tasks that are our best hypothetical learning trajectory of how students might come to emerge with this understanding of proportionality, seeing how proportionality is related to linearity, and that changes in quantities of the linear relationship are proportional, and being able to use that, all these rich connections with constant rate of change and so forth. So they're scaffolded, and so what we've found is as teachers use worksheets, they often become aware of their own understandings, and then they start to reflect on their own understandings in new ways. And then they refine their understandings, even the secondary teachers. And they're perturbed regularly by the questions the students throw out, because they're different than they were when they were using a textbook that focused on getting answers to problems. So this constant perturbation in the classroom we're seeing really wonderful instances of that being a critical element of keeping these, increasing the connections that teachers have. Their scheme for teaching that idea is getting richer and richer all the time. So I guess I think I skipped ahead. Let me just kind of take a detour so that you know a little bit of what I'm talking about. So here is, we might start with looking at a map of proportionality. So first of all, we fleshed out proportionality, and I'll be honest, when we decided we had to put proportionality into the curriculum, Michael Ortman and I spent like 2 years wrestling with what is our theoretical perspective, what does it look like? What kind of ways do we need to engage students in tasks so they build these rich connections of two quantities changing tandem so that they remain in constant ratio, they're related by a constant multiple in a scale, and then seeing how that relates to slope and linearity. So this is kind of a little bit of behind the scenes work that was helpful as we wrote our curriculum. So right now, what I'm going to show you is our current conception of how the type of support teachers need to make these transformations in their own classroom.
Click on products, Marilyn, and save that. There you go.
Okay. So the student has a text. You start with the text for the student. And so first you've got to write something that's going to work for students. One of the characteristics of our pre-calculus curriculum is that we have videos that are our best conceptual explanation with every idea in the entire textbook. So a new teacher can decide, I tell all the teachers the first time through, to watch these videos before they teach.
For the values a quantity can assume.
Whoops. So So they have a textbook, and teachers also have then worksheets that the students use. They have detailed teacher notes. So if there's what we're conjecturing, and this is what the teachers are telling us, although we don't really have research evidence yet, but the teachers read these teacher notes, which is our best effort to pack up all of this that we've learned in 25 years, and the research has told us on what ways of thinking, why did we ask that question? What ways of thinking are we trying to promote? What are the common misconceptions your students might encounter? So in red, online, they can even glance at these right before class. So our earlier research, again, it showed that the teacher's knowledge was just too fragile to act intelligently in the moment. Their fluency with the language was, they stumbled over describing the meaning of average rate of change. So with these notes, they had a constant crutch. So we all know that, like, what it's like to teach calculus for the first time. You stumble all the time, or when you guys go out into the schools, you teach pre-calc or AP calc for the first time. The more supports you have to strengthen your connections and your mathematical knowledge and your pedagogical content knowledge, the better you're going to be able to engage your students. So anyway, our current conjecture is that is one of the primary, that's a critical element of the current success we're having. We also have then, for every worksheet, we have PowerPoints that are basically the same questions that are on the worksheets. And then we have applets that the teacher can use, and we work with them on what kind of conceptual discussion to have around the applets. I'm not sure whether this is the fixed version or not, but as they're two walking together, how would you say Jane and John's trips compare? They both covered the same distance, same amount of time. So what idea are we trying to bring out here?
Average rate of change.
Average rate of change. That, you know, so there's a whole host of questions that a teacher can ask around this applet. I mean, we have one where we just have John walking at a constant rate, and we can do all that scaling and proportional correspondence. And now when we get into average rate of change, calculus students, secondary teachers mostly do not know average rate of change other than it's the slope of the secant line. You know, but the real meaning is, gosh, it's change speed. You're usually taking the average rate of change of some other event, so it's a constant rate you need to go to cover the same distance in the same amount of time. So you can then start to connect it to a graph. Okay, that represents the distance-time relationship of John, and now Jane walked at a constant rate, so they covered the same distance in the same amount of time. So supporting those type of connections has been a key focus of what we're trying to do. This has been probably our module that has, you know, so let me then lead into away from middle school math. So as you look at me pulling the corner on this, what do you see? You see quantities changing together. What's a quantity? Is the fact that it's green a quantity? Is the fact that it's laying on that table a quantity? No, so this notion of a quantity has to have a measurement process. It's something that's measurable. It's an attribute of this box, you know, a side length, and I can measure it. We can have fixed quantities, we can have varying quantities. So if you think about pre-calculus, everything is about relating quantities, right? So once you learn, we spend like 2 or 3 days on this problem, and we have 2 full worksheets, and you can teach, I can teach 3/4 of pre-calculus if I do this problem really, really well. So just to kind of get you to see the type of connections we're trying to support teachers in having. I don't need to tell you what you're looking at here. I know for you all, if you were in Kevin's class, you know what you're looking at. You know, we have students that come into calculus. They don't even know what a cubic unit is. So then, you know, at some point, I can ask you, as I increase the length of the side of the cutout, how does the length of the base of the box change? It gets smaller? Is that enough to write a formula? As I increase the length of the side of the cutout, how does the base of the box change? It decreases by twice as much as what? Cutout. Okay, but what does it decrease from? An 11. So you get two quantities that a student has to conceptualize. Just this simple writing length equal to a fixed quantity 11 minus two varying quantities where x is the length of the side of the cutout. So right there is what we have found repeatedly and repeatedly in studying students' ability to do word problems. Right there is the cognitive move that students are not making. And every textbook I see they don't even attend to it, you know. And so anyway, I won't jump up and down too much about that. So how's the length of the side of the cutout vary with the height of the box? Okay. Yeah, y equal x. You know, so you can even review linear functions, right? So this is the one you just told me to come up with the formula. Length of the base of the box is 11. Oh, initial value of the box. What's this stand for? You know, so you can imagine all the rich connections. What's that point? Oh, it's 0 cutout and it's 11 side. Now, as I increase the length of the side of the cutout from 0 to 1, what happens to the length of the base of the box? And notice this language that we really push throughout because it's what carries the day when they get to trig, polar coordinates. As the length of the side of the cutout increases to 0 to 1, the length of the base of the box decreases by 2 times 1, twice as much. You know, and so you can, we do a lot of this looking at how quantities change together over small intervals, because that's what allows you to graph polar coordinates, sine function, if you want this messy, you know, polynomial, and you can imagine how the quantities change together. One of my PhD students did her dissertation on related rate problems. Right here was the problem. They weren't imagining this dynamical system and imagining how the quantities change together, and in the absence of doing that, they were unable to develop formulas that were meaningful. Okay, I'm going to kind of stop so you all can ask questions here. So kind of with the punchline, I guess. Yeah, so kind of looking at the evolution of a teacher, this is the initial conception. Proportions give a way of finding an unknown value when two fractions are equal, and the value of one variable is unknown. No intervention. Didn't see proportions as being about two varying quantities, did not see how proportionality is connected to linearity, and was not able to locate the y-intercept of a linear function given a point like that. So this teacher, and I think I've got the video, well, I don't. This teacher shifted, and the progression of the shifts were gradual. So over a 3-year period, the first year just working on her own understandings, and then year 2 using her materials, she now can make all of these rich connections in her classrooms with students. And it's been so fun to actually, at this point, be able to start studying success stories of teachers emerging with rich connections. And I would say, you know, well, do they have MKT? Well, what does it mean to have MKT? They're on the road to developing better images of how students learn these key ideas, and also developing better pedagogical tools, because as they have learned how to decenter and attend to student thinking, they develop on the fly of teaching now new pedagogical moves that will allow to put the ball back in the students' court and allow them to struggle with making the connections that are going to allow them to have lasting understanding of the idea instead of intervening in ways where they just tell them the answer. So our current research questions now are, why are these teachers shifting? Which one of the supports is most effective? Are all the teachers equally wonderful? No. But the bar has been raised tremendously in every classroom, because now the tasks promote good things happening. Teachers have tools that they're going to get smarter every day when they teach. And after using the materials, the teachers come back and tell us, oh, the first time using them, I learned more than my students. So just kind of one of the things, a lot of the graduate students that I've met with them today is, how do you get in schools and how do you stay in schools? Well, if good things aren't happening, and even at school that teachers, the principal said, they're here, you know, had good things not started to happen, we would have been probably out the next year. So you've got to have good interventions. And so as all of us are being demanded to collect data, Michael Urban and I, and this instrument is being used, most of the items on it, by the MAA now for a calculus concept readiness. It's been validated, article about it in Cognition and Instruction that came out last year, I think, if you're interested in it. But the pre-calculus concept assessment instrument has been used by me with pre-calc when I taught using old curriculum, and 40 other universities around the nation. And the mean score at the end of pre-calculus was on this 25-item multiple choice exam, where the choices are based on the incorrect reasonings that emerged from research. And now, with pathways, pre-calculus, post-score mean of 15.2. And so that is really beyond what I even thought was possible. So we even had one of our teachers get a post-score of 19 with a group of pre-calculus teachers. We had Don Tusher, one of my colleagues who worked under Bob Ray's, decided to just look at our students that came out of pre-calculus, hard pre-calculus, which those of you that have gone through it, you say, oh, this is all ideas of calculus, but you're just not using the language. They went into BC calculus, and they performed just as well in BC calculus as the whole class of students that had taken AB AP calculus. So they missed a year of calculus, and and we attribute it, to the ways of thinking that emerged and that they practiced during teaching. So the last few minutes, I'll throw out kind of some questions and let you guys ask me questions. But so the big issue is that to look at mathematical content knowledge for teaching, if there's one takeaway, you gotta drill down to that idea, and a lot of people talk about it, in kind of a general sense, and it's not just learning the mathematics. And I guess it's about imagining students learning differently and then being able to act intelligently, to act in ways that are very different in the classroom. So what a lot of NSF money is being put at is more graduate courses for teachers. Yet another course, and I challenge my good friends at U of A and several places around the nation that that are claiming victory because their teachers do better in yet another abstract algebra course for teachers. And I say, you go in the classrooms, and I get feisty with them. I say, you guys are wasting NSF money. If you're not walking in those classrooms to see what kind of ways teachers are interacting with their students, I'm telling you, there's nothing happening. We've got 7 years of nothing happening. And so I just call on those of you that kind of have the math ed bug, that a takeaway with the secondary teachers I think is most problematic. I would love to see many people putting out research-based curriculum and revising it. Kevin and I and team, we're not turning this over to a publisher. It's nonprofit. The schools do have to charge a little bit to pay for the books and to pay for the website. But our idea is this is our research tool now. And so but I think in the absence of teachers having good support materials, the process of change is so slow. It's like a snail's pace, you know, and if you want to change teachers, you know, they can't change it one idea at a time. It's taken me a whole career to understand the ideas of pre-calculus one at a time. So how can we expect a teacher that we're working with to give them a course, and now they're going to write their curriculum? That's hard. I mean, they're not curriculum developers. So anyway, I hope that down the road I'll hear some good stories about some of you having some fun success stories. So at this point, I'll open it up to questions. Does anyone have any questions? Yes.
You spoke a little bit about this, but you were talking about how it's important for the teachers to learn while they're teaching, or I mean, they're going to learn while they're teaching the curriculum. What do you feel like has to be in place in order for the teachers to be able to do that?
Teachers will retreat if the tasks are too hard and they can't manage the conversations in their classroom. So I'm sure there's many more solutions to this problem in addition to what we're having success with. But for us, it was that we had to write the student worksheets. You know, they're scaffolded to ask the questions that I would ask in a clinical interview or a teaching experiment. So it's so they can't do that. The other thing is they have to have these notes because, you know, just because Kevin and I know why we asked it, if the teacher doesn't know what is the critical connection that you're trying to make, they need that information. And so by reading them and then going into the classroom, and then sometimes they fall flat, you know, not horribly because the curriculum holds them up. And I would say the fact that the curriculum holds them up, even if they get in trouble, then they can go to the PowerPoint the first time through. And what we found is they use the PowerPoint the first time through, some of them the second, but the third, not at all, except for those applets. Because as they use the curriculum the second and third time, they've developed so many rich connections they didn't have, so they can become better and better at decentering relative to their students' thinking. And the first time through, they kind of step back and they let the curriculum do more of the work. But so I would say those two things are critical. And then, you know, the homework has to be coherent. You know, if you have, and the students have to succeed. If you develop a curriculum, the homework's too hard, and the students are all complaining, so the homework is very tightly linked to the worksheets. The students are supported so they can succeed. So I think those are all elements that have allowed us to actually get at the point we are where we're seeing some success stories. Any other questions? Yes.
Yeah, I was curious how far, like, I guess how far is it? The curriculum kind of expanded outside of Arizona into Georgia at all or anything like that?
Yeah, I mean, if anybody wants to pilot it in their school, talk to Dr. Moore. And we would love to have new sites. Just this year, we're to the point where all the products are professionally polished. And, you know, so, but our criteria, we do not want a publisher, again, 50 people to use it. You know, so we've got a couple new places in the fall, but we're going to focus on Arizona because now all of these Arizona schools, this is another, you know, indication of success, that they started with 1 or 2 teachers, and then they went to 3 or 4 teachers, and 2 weeks ago we heard that every pre-calculus course in Scottsdale District, Mesa District, as big as Minneapolis-St. Paul, Chandler District, are using the materials. So they took 3 years to say, is this for us? And the teachers are so enthusiastic about what their students are learning, and the data is supporting that. that then now they're asking us to give them the Algebra 2 workbook by the fall. So thank goodness I've been on sabbatical the last year. So we're making some headway on that. And, you know, and what can you say? The teachers are begging for you to help support students in developing like these, you know, about a third of this shouldn't be taught pre-calc. So anyway, so that's kind of the directions we're going. So in answering your question, if anybody and anywhere else wants to use the materials, we do still have some NSF funding, so we come and we give a workshop with the teachers or a few teachers that are using it, because one of our criteria is you can't use the materials unless you go through our workshop. We want everybody to succeed, and that's been really a critical element, is that just working through the materials as if they're students. Okay, any other last questions? Okay, thank you very much.